Hey everyone, this is our presentation on how gas laws affect our daily lives and the effects of gas laws on the human body while climbing Mount Everest.
Yay! It's a pretty cool presentation on how all the air changes as you ascend the mountain and how it affects your body. So it's me, Emily Chevroletti, and Kendall, and Peyton, and Channing actually couldn't be here because we couldn't figure out a scheduling thing to voice over our presentation, so she's actually working on our quiz for you guys. So, yeah, we'll just dive right in.
Okay, so this is just some general information about Mount Everest. Mount Everest is the tallest mountain range in the world, or not mountain range, but mountain. And it's on the border of Nepal and Tibet. Its height is 8,850 meters. And, we focus on meters, not feet, but there's it in feet. And the first person to have climbed Mount Everest, or people, are Edmund Hillary and Tenzing Norgay in 1953. Just some fun facts. And there's a picture of the mountain. Okay, so here we have the different zones of Mount Everest. And first is the base camp. Its altitude is 5,400 meters, and its average atmospheric pressure is 400.4 torr. And the temperature is between negative 18 degrees Celsius and negative 3 degrees Celsius.
And that just depends on the time of year. It just fluctuates so much whether you're in like the summer months or the winter months. And there's actually a website we saw that was talking about, extreme altitudes and different pressures at the different altitudes. And it was talking about how the extreme altitudes, like danger level, started at 5,400 meters, which is kind of where the bottom of the mountain is. So that just shows you the entire hike up the mountain is just crazy.
Okay, and after base camp, we have Camp 1 with an altitude of 6,100 meters, and its average atmospheric pressure is 351 torr. Oh, is it going?
Yeah.
The next camp, Camp 2, with an altitude of 6,500 meters.
This picture is just a different view, more up the back of the mountain. That's why the camp's in a different spot.
Then Camp 3, we have an altitude of 7,400 meters, and you see how on some of these we can't find the average atmospheric pressure because it wasn't provided.
And most hikers don't, carry barometers with them as they hike. That's not their main concern. And the reason we don't have temperatures for any of the camps either is because base camp is the highest altitude of any sort of weather station they have. So any other temperatures recorded at the different camps are kind of arbitrary and are calculated just when climbers bring a thermometer with them.
And then here's Camp 4, otherwise known as the Death Zone, with an altitude of 8,000 meters and an average atmospheric pressure of 283.6 torr. Death Zone. And finally, we're at the summit of the mountain.
Yay!
With an altitude of 8,850 meters, an average atmospheric pressure of 253 torrs, and now we have a temperature again of negative 35 degrees Celsius to negative 20 degrees Celsius.
And all of these calculations that we have, the only time that any of the air pressures were recorded on Mount Everest were actually in 1981. And so you'll see later when we start doing some calculations with the gas laws that some of the values are quite a bit off from these measurements, and a lot of them have to do with the fact that they were used with older technology and they were taking the values were taken such a long time ago. Well, not really that long. I didn't mean that. But, they were just taken a while ago, so they're not current or measured with modern technology. Okay, and now we're into the part where we actually start applying the gas laws to what happens on Mount Everest. So we know that as you ascend Mount Everest, the pressure decreases, and so does the temperature. And these atmospheric conditions can actually be represented through the formula for the Gay-Lussac gas law, which is a formula that shows the direct relationship between pressure and temperature. So pressure over temperature is equal to pressure over temperature, and just a different set of conditions for the actual air surrounding the mountain. Okay, so now with that formula in mind, we are going to do some practice. So here's the formula again, just so you can see it. Okay, so the first stone on the mountain at base camp, we showed you that the average air pressure is about 400.4 torr. And the temperature fluctuates so much throughout the year, but in May, the temperature at base camp is about negative 7 degrees Celsius. Also in May, the temperature at the summit of the mountain is negative 25 degrees Celsius, so we're going to calculate the air pressure in torr at the summit. Okay, so we're going to do this, so we're going to set it up, you know the formula, so our pressure 1 is 400.4 torr, that's at the base camp, and the base camp temperature is, we said, negative 7 degrees Celsius. Remember, we have to convert that to Kelvin to use the gas laws, and so when we add 273, we will get 266 Kelvin. And this is set up in our ratio, and we're looking for our pressure 2, the pressure at the summit, and when we convert 25 degrees Celsius to Kelvin, we're going to get 248 Kelvin. So we're going to divide these, and then to get P2 by itself, we'll multiply this after we divide these. And you can pause this if you want to do the math. And then our pressure 2 will be 373. Now, if you remember back to the other slides, the actual pressure at the top of the mountain is actually 253. So you can see that that's a pretty big difference. But like we said earlier, there's only ever been one recorded pressure at the top of the mountain here. Up there, that's my Everest things. Here, there's the mountain. Okay, so there's only ever been one at the top of the mountain, and it was used a pocket barometer. So just something that a hiker happened to have on them and happened to, try and take a reading while they're at the top of the mountain. It's not what I would do if I climbed Mount Everest. It's not the first thing I would do when I got to the top. But anyway, so the actual reading could have been slightly inaccurate, but this calculation I just wanted to be able to do with you guys so you get the idea of the actual, the ratio that happens between the two different sections. Okay, so now we're going to see how this kind of applies to the body, since that's what our presentation is all about. So as we've proven through the Gay-Lussac law, you can see that the air gets thinner as you travel upwards. So even though that ratio that we got for the second pressure at the top of the mountain wasn't exactly what the reading said it was supposed to be, it was still lower than the original pressure at the bottom of the mountain. So the air does get thinner as you travel up Mount Everest, and because of this, the body has a much more difficult time getting enough oxygen, and it tries to compensate in different ways. So the actual ratio of oxygen and other gas remains the same, and as Kendall will explain later, the percentage of oxygen in the air is 21%, O2 in the air. And so at sea level, it's the highest possible oxygen composition. So the highest possible oxygen composition is this 21%. So if we're pretending this 21% is the full value, it'd be 100% of that 21. Well, as we move up the mountain, even up to base camp, it's still only 51%. So almost, it's about 10% of the total air if we move that to this ratio up here, and the further up you go. And so at the top of the mountain, at the summit, it's only 33% of this 21% up here that is actually in the air, because because the composition is changing, the pressure is decreasing even more, which is obviously not good because you kind of need oxygen. Okay, so now we're going to move on to Boyles Law, which is another law that applies to climbing Mount Everest. So as you saw in the previous slide, the oxygen available in the air kind of changes, and so the lungs have to adapt to this changing amount of oxygen. So we can actually use Boyles Law between pressure and volume and their indirect relationship in order to actually see how much the lung capacity can change as you climb the mountain. All right, so we're going to just go ahead and jump right on into practice again with Boyles Law. So a normal full-grown man has a lung capacity of 6 liters. That's actually quite a bit. And so we know that at sea level, the standard air pressure, STP, is, 760 torr, or 1 atm. And the air pressure at the mountain summit is 253 torr. Or that's the last measured air pressure. And so we want to find out what capacity the man's lungs can have at the greater altitude of the summit. Okay, so I'm going to rewrite the formula again. We know it's P1 V1 equals P2 V2. So our first pressure is 760 torr. That's like at what would be at sea level, and our first volume is 6 liters. We know that our second pressure at like the summit of Mount Everest is 253 torr, and we are looking for volume 2. So if you multiply these together and then divide by this one, you will see that your second volume about 18 liters. And that's a lot. That's crazy. But you think of, the big decrease in air pressure. I mean, you see the difference between 760 at sea level and 253 at the top of the mountain. And so because this increase in air pressure, the air is so much thinner that your body can just fill up more space in it. I mean, even 6 liters seems like so much to me. But if you think about it and you take just a really, really deep breath, I mean, it's like so big that like you feel like your lungs hurt. I mean, that can actually fill in a lot of air into all the little alveoli of the lungs. Okay, and I just want to give one more example of Boyles' Law that accounts to something else in the body. So it also can help explain why many mountain climbers battle altitude sickness, which is something that happens when you ascend a mountain too fast and you're changing in altitude too much similar to why like deep sea divers get the bends, if they're changing water pressure too fast. So at a higher altitude, the heart actually functions better. That means that it can actually pump harder and faster. But the downside of this is that there's an overabundance of red blood cells in the bloodstream. And this picture, it'll make more sense in a minute, but what happens is when you get altitude sickness, they have to change the pressure around your body to get you better, and so they put you in one of these hyperbaric bags so that it can actually adjust the pressure around you to slow down the effects of altitude sickness. And so this slide explains why they have to put you in that hyperbaric bag. Basically, within the blood cells are little pockets of oxygen. You can see the oxygen from lungs enters the blood cells, and then it bonds with the hemoglobin molecules inside the red blood cells. And these travel throughout the body. But when the external air pressure on the body, this is the body, and you have all this air pressure out here, if it decreases, if it drops, like we know it does as you go up the mountain, according to Boyles' Law, when pressure goes down, volume goes up. So what happens is these oxygen molecules actually expand. Like their volume literally increases and each molecule literally expands. It can cause the blood to become thicker, and actually the blood itself can seep out of the blood vessels and into the body cavity. And because the oxygen is taking up such a big portion of your blood, it causes altitude sickness and can cause nausea, fatigue, headaches. It can kind of lead to like a drunkenness kind of feeling, and shortness of breath is the main thing in causing fluid to actually build up in the lining of the brain and of the lungs, which is obviously not good. And so whenever this happens, there's an extreme chance of death, especially when you're high up on the mountain. But the air is so thin that helicopters actually can't even function at the altitude. And so the only hope is for your teammates, when you climb with a team, to actually get you in a hyperbaric bag so that they can readjust the pressure around you to kind of increase it more to get the oxygen level to go down in your bloodstream so that the altitude sickness will go away until they can get you to move further down the mountain and get you to medical help. And I actually know all this because I actually, in middle school, I had a random obsession with Mount Everest. I had to do a project once, and I just thought it was so cool. So I read all these books about people who had climbed it, and all these stories about the things that happened. And I watched this movie called Vertical Limit, which they got stuck in an avalanche on the mountain, and they had to do almost all of these things to avoid altitude sickness. So I thought it's really cool knowing that there's actually scientific reasons why all of those things happen.
Okay, so next we're going to talk about Dalton's law of partial pressures, which deals with gas mixtures rather than just singular gases. The partial pressure of a gas is the amount of pressure that each individual gas in a mixture would exert if it occupied the volume by itself. So just on its own, the pressure that it would exert in the same volume. According to Dalton's law, the total pressure exerted by a mixture is the sum of all the partial pressures, and that's because there are no intermolecular attractions between the gases, so they're not pushing each other down or messing with each other at all within the mixture. They're just all existing within the mixture. And so that's represented by this formula, which is the total pressure equals each individual pressure added together, each partial pressure added together. Okay, you can also use mole fractions to determine the partial pressure of a gas within a mixture. This formula that I've written here is actually, wrong. It should be P, the partial pressure of a gas, equals the total pressure times the mole fraction. Basically what that's saying there is that the number of moles, or the mole ratio in a gas mixture, should be basically equivalent to the pressure ratio, in that if you have, say, 50 moles within 100 moles total, you would have a mole fraction of 0.5, and just the same you would have if you have a total pressure of 100 and a partial pressure of 50. The partial pressure would also be 0.5 in that equation. That was a confusing explanation at the end there, but basically that should help you find partial pressures because they should be the same. Okay, so what that means about the air we breathe. Oxygen makes up only 21% of the atmospheric air, I guess it would be. And so based on that, the partial pressure of oxygen within the mixture must also be 21% of the total pressure of the mixture. Because it basically means there's about 21 moles of oxygen for 100 moles of air. And so at sea level, where the normal atmospheric pressure is 1 atmosphere or 760 torr, the partial pressure of oxygen alone would be 0.21 atmospheres or 159.6 torr, which is important to remember. So as you continue up Mount Everest, the total pressure exerted by the air will decrease. As we showed in our earlier slides, as you get to the summit, the pressure is about 400.4 torr or 0.51 atmospheres at the base camp, and 250, I'm not going to circle it because that's going to be annoying, 253 torr or about 0.33 atmospheres at the summit. So, using Dalton's law, the partial pressure of oxygen as you ascend Mount Everest must also decrease because the total pressure is decreasing. So the amount of oxygen available for us to breathe when we get higher up on Mount Everest decreases significantly as you keep going. So at base camp, oxygen is only approximately 0.11, that was a weird way to say it, 0.11 atmospheres of pressure, or only exerting about 0.11 atmospheres of pressure, which is significantly lower than at base camp, or even not at base camp, at sea level. And at the summit, it's only exerting about 0.07 atmospheres, which is extremely low and often attributes to a lot of the problems that you face when you get up to the summit, and often you need.
And there was a statistic that we found where anytime the partial pressure of oxygen gets anything lower than 0.1, it's actually extremely, extremely dangerous for the body. And so you can see at the summit being 0.7. I mean, even base camp is pretty much at the limit. And so that's why most people climb the mountain with oxygen tanks.
Yes. Okay, so here's some quick and easy basic practice with Dalton's Law, dealing with the changes in total pressure as you go up the mountain. As you reach about Camp 4 of Mount Everest, which is roughly 8,000 meters, nitrogen exerts a partial pressure of 221.2 torr. Whoops, that's not a 1. Now it's a 1. Okay. Oxygen then exerts a partial pressure of about 59.6 torr. Writing's fun. And the remaining gases, which are much smaller, exert a combined partial pressure of about 2.8 torr. So using Dalton's Law and these figures, what is the total pressure exerted by air at Camp 4? Okay, so we're going to continue that calculation over here because there was no room on that other slide. So the the total pressure, according to Dalton's Law, equals, wow, writing on this is no fun, equals the combined sum of the partial pressures that we talked about earlier. I'm just going to call that the partial pressure of X because those gases were a very small proportion of air and were unnecessary to name at the time. Okay, so if you recall from the last slide, the partial pressure of nitrogen was 221.2, the partial pressure of oxygen was 59.6, and the partial pressure of the remaining gases was 2.8 torr. So, in order to find the total pressure, all you have to do is add these together. It's very simple. Yay, it's very fun to watch. Having a blast writing it as well. Yep. Yes. Indeed. Alright, and so when you add all those together, you should get a total pressure of about 283.6 torr, which, if you recall from an earlier slide, is the atmospheric pressure at Camp 4 that we gave. Okay, so to wrap up Dalton's Law with a bit of relevance to our actual presentation, its impact on the body. As you ascend, again, oxygen, or the total amount, or the total pressure exerted by air decreases, which means the partial pressure exerted by oxygen decreases. I don't know if you know this, but oxygen is a pretty essential part of most bodily functions, especially our neural and muscular function. So according to Dalton's Law, the pressure exerted by oxygen decreases as you ascend Mount Everest, which means you are, in all, intaking less oxygen than you would be if you were at the atmospheric pressure we're used to, or even if you were at sea level. So, a couple of things that this does to the body. Oxygen, first of all, provides the energy source for our muscles. The oxidation, or the oxygen, which is a word I know, the oxygen in blood travels to our muscles and allows it to refuel itself with ATP through aerobic respiration, which is a whole very specific process that I'm not going to get into. But basically what's happening is less oxygen is traveling through the bloodstream to the muscles. And so the muscles have to perform anaerobic respiration without oxygen, and then they're going to fatigue easier and develop lactic acid, and it's going to hurt to climb, and it's just going to get a lot harder overall to get yourself up that mountain, and also just breathe in general, which sucks because breathing is necessary for most everything living, basically. Okay. Also, lack of oxygen will impair your neurological function, and no, it's not good at all. And this tends to make people, it's harder to think, and judgment actually starts to fail a little bit, a bit like being drunk. You can't quite make the right decisions, and so that's never good when you're in a high-risk situation. And so it's very dangerous to continue to climb up because you have less oxygen intake, and so it becomes incredibly imperative, as we said earlier, that you supplement your oxygen.
Although there are, all those daredevils that like to climb the mountain without oxygen, and they're just crazy and unnatural.
And that's why Camp 4 is called the death zone.
Yeah, because it has the least amount of oxygen of all of them. So anyway, that is our presentation.
Yep. Peyton doesn't want to talk.
Okay. Well, I hope you learned something, because
we sure did.
that's not cheesy. Okay, guys.
All right, that's it. We're going to stop now.